All right, this is a video for geometry on perpendicular and angle bisectors. We'll start with perpendicular bisectors, looking at a theorem, do an example or two, and then we'll switch to angle bisectors and do the same. So the theorem for the perpendicular bisector theorem is pretty powerful, pretty useful, and has some really interesting real-world connections. So if we happen to have a perpendicular bisector, so that's what we're given, okay? So the vertical line on your screen is the perpendicular bisector of line segment AB. Okay. If we know that is true, then we can conclude that every point on that line, wherever we happen to draw our points, would be equidistant to A and B. Okay, and this feels intuitive because of just the symmetry associated with a perpendicular bisector, and it is pretty intuitive, but you get a pretty useful result here. So any point we choose anywhere along that vertical perpendicular bisector line is going to be equidistant to the endpoints of that line segment. And the neat thing here is, let me draw my angle implying a conditional statement, or my arrow. The neat thing here is that the converse is also true. So if we are given the stuff on the right, if we are given that every point along that line is equidistant to the endpoints of the segment, watch, I'm going to draw a double-headed arrow. That then implies that we're working with a perpendicular bisector. So the converse is also true. So this theorem kind of goes in both directions. Okay, super useful. And let's apply this right now. So we have a particular triangle right here. It looks like we do have a perpendicular bisector. This segment AC is being bisected by line BD. And so that means that AB must be congruent to BC. Okay, so these two distances must be equal. So we can write out an algebraic statement and simply say that 4x must be equal to 6x minus 10. And let's solve for x. So I will subtract 6x from both sides to clump all my x's over on the left. I get a negative 2x is equal to negative 10. I'll divide by negative 2. X is equal to 5. Okay. The problem actually, it's not specified here, but the problem would probably ask for not just what x is, but what's the length of the line segment. So AB would have a length of 4 times 5, which is 20 units. All right, and then in a real world scenario, this is a hypothetical visual map of an amusement park with some rides, some boats, some merry-go-rounds and stuff. So let's say you have the opportunity to make it maybe put in a business. Maybe you're building a t-shirt shop or something, and you want to sell t-shirts in a place that's accessible, perhaps to people who are doing paddle boats and then also doing the merry-go-round. Okay, so you want a t-shirt shop to be equidistant to people who are using the paddle boats and using the merry-go-round. That doesn't mean it has to be exactly halfway in between. We just know that it has to be equidistant. So let's draw a line segment between the paddle boats and the merry-go-round, and then we will draw a perpendicular bisector. Okay. And if that is a perpendicular bisector, and now that it's labeled, it is, we could have our t-shirt shop anywhere along that line. Okay. So anywhere along that line would meet the requirements we want of making sure our t-shirt shop is equidistant to the paddle boats and the merry-go-round. Now, let's say there was another requirement that you also wanted your t-shirt shop to be equidistant to between the merry-go-round and the spaceship. Okay, so let's do this in a different color here. You wanted equal access to those pieces, or to those points in the amusement park. So let's draw another angle bisector, or perpendicular bisector. All right, and so this is a perpendicular bisector here. Okay, and anywhere along this green line, your patrons would have equal access to the spaceship, chute, and the merry-go-round. Now the thing to think about is there a particular location where your patrons would have equal access to all three parts of the amusement park: the paddle boats, the spaceship chute, and the merry-go-round. And that would be, the answer is yes, that would be at this point right here. Okay, so at that point, the distance to the paddle boats would be equidistant to the merry-go-round, which would also be equidistant to the spaceship chute. Okay, so if you wanted equal access to all of those rides from your t-shirt shop, that would be the place to do it. Let's switch to thinking about the angle bisector theorem. Okay, and as you can see in the title here, the converse will also be true. So this will be another double arrow conditional statement. Okay, but let's start off with just the given on the left that we know we have an angle bisector. Okay, that's what we're given. What can we conclude? We can conclude that any point along that angle bisector is equidistant to the sides of the angle. And when we talk about the distance between a point and a line, we're talking about the perpendicular distance. Okay, so there's a particular point we need to reach with that line. So any point that we choose along the angle bisector would be equidistant to the sides of the angle. Okay, and so as I said before, the converse is also true. So if we are given this information, if we are given the fact that we have a line that is equidistant to two other sides of an angle perhaps, then we would know that must be an angle bisector. Okay, so the converse is also true. Let's apply this and then we'll summarize what we've done so far. So what we're given here is an angle bisector. That's what those marks mean around angle N. And we're looking for the lengths from a particular point R on the angle bisector out to the sides of the angle. So the angle bisector theorem says that those two segments must be equal in length or congruent. So we can write out 7x is equal to 2x plus 25. Subtract 2x from both sides, we get 5x is 25, and divide by 5, we'll get x is equal to 5. And as always, we're not necessarily looking for just what x is. Let's find the length of one of those line segments. So the length of MR is 7 times 5, which is 35 units. I want to summarize this and give you a little bit more information on what happens when you construct these things in triangles. Okay, and this is pretty useful, pretty interesting here. So let's work with perpendicular bisectors first. If you draw all three perpendicular bisectors in a particular triangle, and here they're not officially being labeled as being bisectors, so I will label that like so. Try not to clutter up the diagram too much. Those will always all meet at a particular point, okay, which is kind of surprising, I would think. You know, it's kind of unusual for three lines to meet all at one point, but they always will, no matter what triangle you have. And this is called the circumcenter. The circumcenter is the center of the triangle, or excuse me, the center of the circle that goes through, let's see if I can get this to work here. The center of the circle that goes through all three vertices. Okay, so I'm not exactly matching it, but I'm pretty close. So that circle I just drew, its center is the circumcenter, and that circle will go through all three vertices of the triangle. That's called a circumscribed circle. Let's look at the angle bisectors now in a triangle. If you draw all three angle bisectors in any triangle, They will meet at a point called the at a point called the incenter. And again, these lines will always meet at one particular point. And this center is actually the center of the inscribed circle. So if we try to draw a circle that just barely hits each of the sides of the triangle, the center of that circle would be the incenter. All right, so some pretty powerful, pretty useful stuff just from perpendiculars and angle bisectors in a triangle. And that's a great place to stop.